Hello, and welcome to this introductory video on Maxwell's equations and light. In this video, we're going to at least sort of conceptually describe Maxwell's equations and link them to this idea of light and say how it is that we believe light really exists and propagates. So when we think about Maxwell's equations, you may have seen them before. They might look a little bit daunting in terms of the actual equations themselves, but what we're going to do, as I said, is present them in a nice conceptual way using some words. So basically, the first of Maxwell's equations summarizes what we already know. In fact, all four of them summarize the sort of ideas that you pick up in a basic electricity and magnetism unit, and we've covered all of these in the videos as well. So what's going on is the first one is summarizing what we know about electric fields. So in the electrostatics case, you talk about electric field lines as only ones that appear or originate from the positive charges, and they terminate and disappear or end on negative charges. So that means that they are sourced by charges. And then further, we also learned that the strength of that electric field that we are describing by these field lines is related to this constant epsilon naught, the permittivity of free space. The second law is the sort of analogous statement for magnetic fields instead of electric fields. And there, remember, we had sort of the opposite case. We had no beginning or end of a magnetic field line, and that's actually vital. It ends up being the statement that if you've got to form a closed loop, there's no sort of isolated north or isolated south pole that could originate those fields. So we saw for permanent magnets or even coils where you could think about having a north and south end, that those north and south poles were always paired. And this law, or the second equation here, is just summarizing that fact that they always have to be paired. There's no monopole, meaning there's no single north pole by itself somewhere and the south pole somewhere else, completely isolated. Right. And then further, if we think about all the stuff that we were doing, we know that the strength of that field is related to the constant mu naught, which was the permeability of free space. Then the third one is talking about the fact that if we have a changing magnetic field, then we can create an electric field. So that was what we saw in terms of the last bit of discussion with like Faraday's law and Lenz's law put together. We were looking at exactly this. The changing magnetic flux was resulting in an electric field, which was basically looping around and giving rise to this EMF that then allowed current to flow in another loop that was subjected to that changing magnetic field. And then there's an analogous statement that actually you can do a changing electric field to create a magnetic field. And that sounds like something new, but it's not. We talked about it originally in terms of charges that were moving. So we said currents create magnetic fields, but that's exactly what that says. If I've got a current, I've got a charge which is moving along. It's dragging its electric field with it. And so certainly that is a changing electric field. Okay? So changing electric fields do create magnetic fields. That is a summary of what the equations actually mean. Now, there's another interesting consequence. Those two constants, the vacuum permeability and the vacuum permittivity, combine to give the speed of light, according to this equation here, that the speed of light is actually just 1 on the square root of the product of those constants. So it's not a coincidence. It's actually because of fundamental underlying physics that those constants combine to give the speed of light. And the reason for that is the fact that light is actually a collection of oscillating electric and magnetic fields. So this is what a light propagating along this green direction here looks like. We have an oscillating, say, E field, which is going up and down, and we've got a B field going up and down perpendicular to that. This is the structure of light, that you have these electric and magnetic fields which are perpendicular to each other and perpendicular to the direction of propagation of the wave, progressing along in this manner. And so, since the E field is related to the epsilon naught and the B field involves mu naught all the time, shouldn't be too surprising that the speed of light comes out of this thing. If you want to see what the equations are, this is what they look like. Now, you don't need to understand them, but these are indeed Maxwell's equations, and these things here are divergences. They do, in fact, mean exactly this kind of statement about what is the beginning and end of a field line. And then these ones here involving the curls are exactly looking at these time derivatives, so giving us the changing magnetic field causing electric fields that curl around them. That's why we have a curl operator. I won't say more about that. And similarly, that magnetic field curls around the changing electric field, which was our current originally. And that's what that equation encapsulates there.